Well, I would like to thank the organizers for inviting me to this nice event. And before I begin, I would like to apologize in advance because some of my videos will not be correctly displayed in the presentation. Then I will have to switch to another window and something like that, okay? Then now, today we are going to speak about interatomic potentials. Actually, I'm going to focus my presentation on reactive potentials. And I will talk about first, second, and third generations in the cases when this makes some sense. Okay, in some cases we don't have this kind of classification. Okay, then here in a outline of the presentation. First, a brief introduction. I will comment about the first models, some of the first, because there are many. Then I will briefly explain in a really simple way the non-reactive potentials in order to be able to compare with the reactive potentials, and then talk a little more about the React-FF and some applications of this nice potential that I've been using for a few years. Okay. Now, the idea is always that we want to describe several different scales of systems, from small molecules to large molecules, macromolecules, or infinite systems, or you see here graphene and things like that. Then we are looking for techniques that are able to deal with all these scales, right? Typically, we are trying to make some kind of atomistic description. Then we have here some atoms represented. Then one atom can, if it is moving, then we can have some kind of dragging force. Then a random force that would be maybe the thermal agitation. And to understand what happens between the particles, we should define some kind of interaction potential to understand how one particle see the others, and vice versa, okay? Then typically we consider that the best way to do that would be to use quantum mechanical methods, of course, because it's physically consistent, describes all mechanical, electronic, and optical properties, but the problem is the scaling on the computation part, right? It goes with n to the cube or worse, and then we will reach always a size limit, typically a few hundred atoms, but in some approximations you can go up to some thousands of atoms. Always this is connected with, of course, your computing power. And on the other side, we have the empirical force fields, where we can treat the particles as classical particles, and then we don't have any explicit electrons. And then the idea is that we construct functions that try to mimetize the quantum behavior that you observe when you do similar simulation using quantum mechanics. And these functions must be chosen with some care, because they should change the behavior depending on the environment, on the chemical environment that the atom is included. And then the complexity and the quality of the results will depend on this set of functions, but this kind of approach is efficient computationally. And the functional parameters usually you can fit by the use of quantum methods also, typically DFT. Then we have many possible formulations, and I will talk a little bit about this. Just to set the scale in length, and time that we are dealing with will be somewhere here when you are using the the reactive potentials, right? Okay, just to comment. From nanometers, a little bit further, and from picoseconds maybe to nanoseconds or something like that. Then here, just to emphasize the relevance of this kind of approach, why molecular dynamics is always a nice tool because it can complement experimental studies. It can be used for fast testing of some hypotheses that you have about the system. You can reach some atomistic details that are not accessible by experiments, like if you have a chemical reaction, sometimes you would like to know what are the intermediate compounds that we have that are not stable, but they, at some point, they are formed. With this kind of approach, we can see those. Then you also can access conditions that are difficult or maybe impossible to do in the experiment and to try other possibilities. And usually when you do some classical simulation, it is usually much cheaper than doing experiments for many, many cases. Then, then now we can start talking about the first experience that people did with molecular dynamic simulations. It started actually around the 1950s. In late 1950s, some people did some computational molecular dynamics simulations, and typically they used the Lennard-Jones potential to describe gases or fluids, and they noted that it was easy to set up a microcanonical ensemble for the simulations. And later, after the definition of thermostats, people were able to control temperature, pressure, to study very well the diffusion and so on. But Lennard-Jones potential was perceived as something that is not good for solids or to describe covalent bonded systems. Then it was obvious that we needed some more complex potential to deal with this kind of system. And many propositions were made in the following years. But here I will show just a few of them, those that I think that are more relevant, and then you will see that many of them come from the same place. Okay. One option that appeared in 1983 was the EM method. It is used up to now. Many people like to use this potential, but it has an interesting thing that is the embedding energy, because it depends on the atomic electron density, and we have a contribution of a pair potential interaction. Then this term here is related to the chemical environment, and it's something that is different from the Lennard-Jones option, for example. And this is maybe the great thing of EAN. And then we have after that the MEAN. That is a modification in which were included some angle-dependent terms to try to describe better covalent materials and similar. But the great force of this method, in my vision, is to treat metals and alloys, and the computation is not expensive, but brittle materials usually are not so well described for this potential, actually. Okay, then on the other side we have, okay, then here you have this comment, the chemical environment matters. Then we have on the other side classical force fields that are not reactive in this case. And for this kind of description, we have an important feature here. We have the potential. This potential is made with several contributions. One, in this example, a spring force term, angles between bonds term, a torsion terms, and a non-bonded interaction term that includes Lennard-Jones and Coulomb. The important thing here to see is that when you have the spring term for the bond stretching, we see that no matter the length of the bond that you put here, it will never break. Then if you start with some connectivity, it will last until the end of the simulation, right? Then that's why this kind of potential is not a reactive one. You cannot change the connectivity of the atoms. And this is what I'm arguing that, well, this is the reason why this is not reactive, right? Sorry.
So if you have two different cations or ion cation, the only repulsive part that you have is the one that comes from the Lennard-Jones.
Typically, yes. And here, the main problem is this of the connectivity, and we have another problem. If you have, for example, like in carbon, the possibility of single, double, or triple bonds, you must have 3 KB constants. Then you have to create 3 kinds of carbon. Then if you have many atoms, many elements, and each element has many kinds of connections, and then you must have hundreds of parameters for the system, right? Then it's something that's not quite comfortable in some moments, right? Then other classical force fields have the same kind of issue, but it's for their nature. It doesn't mean that they are not good, right? They are they are used a lot and with really nice results. The only question is that you cannot do simulations where you expect to see some chemical reactions. That's okay. But if you want to see diffusion or some kind of rearrangement, to find the ground state configuration, it's okay. But you just cannot expect to describe chemical reactions with this kind of potential. Okay, and then this is the paradigm of a lot of them, right? And I will not focus on this kind of potential today. Before we speak explicitly about the reactive potentials, you can see here the general structure that we usually include, we adopt. We have a general potential that is made out of several contributions. One for stretching, other for angles between bonds, and 4 body terms that are used to describe energy of dihedral angles or improper angles, and then you can put many body interactions of other kinds. It depends on the type of situation you want to describe, okay? The question here is that we must think about some way to include the possibility of breaking the connections. And this will be done using the bond order parameter, okay? Then we'll talk about this now. One of the first reactive potentials that was used is this kind. Usually when someone is talking about reactive fields, they start talking about the Stillinger-Weber. It has a 2-body term and a cutoff function for the other contributions, for the three-body contributions. Okay, here one first thing is this cutoff function that cuts the interaction after some kind of distance. And the more important contribution that was made in 1985 was this potential by Abel. And this structure is used until today in some sense. The idea is that you have a VR that is a repulsive part of the potential, and VA that would be a attractive part of the potential, and the attractive part is controlled by the BIJ. This is the bond order. Then it defines, for example, if you have a carbon, in a few minutes we will see a calculation of the bond order for a carbon-carbon connection. Okay. Then if you have some distance, some big distance between two carbons, you have a bond order of 1, that it would be the sigma contribution. Then if you have some shorter distance, you have sigma and a pi contribution, making a double bond. And that is controlled by the bond order parameter that we calculate. And then you can have also the 3 bond order. And we will see later. But this is the idea. Then after this proposition, many other potentials came with this kind of structure. And also we have here a cutoff function. Okay. Let's see. Then this Tersov, there is a potential that, despite of its age, it was proposed in 1986, but it can be used even today and with good results in many situations. And it follows the same structure, okay? A repulsive part, an attractive part, then we have the bond order here, and a cutting function that is well chosen also. The idea here is that the bond order is always integrated in the potential. This is the great contribution of these guys, Abel and Tersov. Then here, the idea you see, it's quite similar to the idea of Abel. But Tersov worked a little bit harder to define this bond order in a empirical sense that worked well with the experiments. And it's amazing how it works well for many situations in silicon, germanium, carbon, and it could be extended, but typically we use this, just a few elements with this potential, okay? Then after this initial phase, that where we had many things happening and many propositions on the market, this was the one, in my opinion, that was most important, because after this, all the good potentials were made based on this one. And you will see some options of that. Here, there is one that was dislocated in time in some sense, because it came later. It's the EDIP potential, that is also a reactive potential, really, and works really nice for liquids, liquid carbon, for example, and some amorphous materials, and it was made by Professor Justo of USP. But for some reason, they didn't develop it much further after the 90s. Okay, but it's something that would be really nice if someone is interested in working with. And the idea here is also that you have contributions of 2 bodies, 3 bodies, and then we have a cutting function, the effective coordination, then you control the connectivity using some function that goes smoothly to 0 at some point. But coming back in time, one of the greatest potentials that appeared was the Ribot. Right? Then you see that here, again, the same structure used by Abel and Tersov. We have a repulsive contribution and attractive contribution, and B, that would be the bond order term. The effective cutoff is essentially the same used by Tersov, but the bond order is calculated in a complicated way. And this potential also is amazing. It works very well for carbon. For many situations, it produces vibration in some cases. Yes. In here, we have a mixing of things, okay? You make both things. Sometimes you have a structure that you know using quantum mechanics, and then you adjust your parameters to agree with that. Typically, that's the case, even for the more advanced potentials that we have today. Most of the time, you use DFT. But if you can compare in some case with experiment, it's better, of course. Right? Let's see. Then you have the cutoff, as I said, and it has a good transferability. What is the meaning of transferability? It means that if you made the parameterization using some kind of system, but for some reason, when you make calculations with systems different from those that you use it in the parameterization, it works well. This is transferability. Then, not always it happens, but for some potentials it happens more often than to others. Then you have the second generation of the Ribble family. Then we have the Ribble 2 in 2002. The idea was to, again, use the same switching function, but changing something on the bond order, and including, in this case, the dihedral angles, the four-body terms. It's not so used as the other one that I included in the second generation, that is the I-Ribble potential. It's also a Ribble potential with the same structure. And then we have a Lennard-Jones intermolecular potential included, but it's controlled by this adaptive treatment here. We have this function S, where theta is the Heaviside function, the step function of Heaviside, and it's a complicated function that controls the action of the Lennard-Jones potential. Okay, this would be the second generation. Then after this, we have a really nice potential that appeared in 2007. That would be the COMB, charge optimized many body potentials. Actually, the name can be used for many parameterizations that are similar. The idea of Susan Sinot was to get this Iyazukawa potential that is nothing more than a Tersov with self-consistent charge and some electrostatic term, and improved this proposition of Iyazukawa. The idea was to improve the charge equilibration procedure. That is something that is not so simple. Usually you had how to do that. The idea is the following. If you have in a system atoms that have different electroaffinity, you know that if they are bonded, you have some kind of charge transfer from one to the other. And in the potentials that I discussed until now, it was not taken into account. Then you can make some mistakes in some cases, right? And you cannot describe polarizabilities also for the systems if you have something that it ignores the charge. And here the idea is that you try to maintain the system as a whole neutrally charged, okay, charge 0 in the total, but each atom can have a excess or some depleted charge. Then to calculate that, you make a procedure that usually means more than 50% of the calculation time, of the computation time. in which you try to minimize the electrostatic energy. And this procedure can be made in many, many ways. One of the ways is this one that was chosen by Susan, in which you define a Lagrangian, in which the charge is included as one of the variables. And this is quite interesting, because if you construct a good Lagrangian with this, as we know, the Lagrangian can be used to find a variational problem, and then if you solve this variational problem, you have the actual charge that minimize the electrostatic energy. Okay. The other way would be to make some kind of self-consistent calculation, which you use initial charge and then substitute again and again in the equations. But usually this can takes a long time also. Then this, despite the fact that in many articles, when you read, people ignore this part, this sometimes is the biggest computational problem that we have. Then getting this improved Tersoff that was made by Yasukawa, they improved the charge equilibration, changed this bonding term that is nothing more than a three-body term, and made some corrections to the repulsive energy. This is something that always happens. When you go from one generation to the other, people try to change some functions to, and what is the criteria to change these functions? You are trying to agree with experimental or quantum mechanical curves. That's the idea. That sometimes you don't have a really good reason, physical or chemical reason, to change some part of the function, but you see that it will be more suitable for the data. And sometimes you have some intuition that guides you in this. And this comb potential is really powerful, really sophisticated, the formulation. This paper is really nice to read. And they could make initially a nice description for this interface between silicon and silicon oxide. And they describe it really nicely, the charge transfer and many-body effects. Okay. Then we have the second generation of comb. Comb has 3 generations, but the second generation was came with a little bit of problem, because they had to divide it in 2 branches, and none of them worked so well because they are not too much transferable, as I explained it for you. What happens is that today we have the 3rd generation comb. That is an improvement on the second one, and then several problems were solved. I don't know all the details, but the idea is that they change a little bit some functional forms again. They were able to increase the flexibility for various environments, then it's more transferable, and then they improved also the coordination function, or that bonding term that I explained before. Then here, in other options, we always had one, let's see, usually you have one bond order term, right? Like here. In this case, they have 4 of them. One connected to angle, to coordination, to torsion, and to conjugation. Then with these improvements, they were able to expand the description for more complex systems. For example, here we can see the metallocene made out with copper. Here the colors indicate the charges, okay? The red are positive, blue are negative charges. Then you see the metallocene of copper being, it can be dissociated, and comb 3rd generation describes it quite well. Here we have a CH3, CH2 molecule when it finds a metallic surface, and then we see some charge transfer, and the dissociation of this molecule is catalyzed by by this metallic surface. Okay, it's also something nice to see. Now we are going to talk about the biggest competitor of COMB, that is React-FF potential. I have some more experience with this one. Then I will dig a little bit more in detail in this case. Well, here we have some features. We have non-bonded interactions as van der Waals and Coulomb calculated for all pairs of atoms on this system. All the connectivity-dependent interactions are also bond order dependent, as in the other other potentials that we discussed. Obviously, their contributions disappear with bond dissociation. We have the charge calculation scheme also. No discontinuities in energy. And here is one of the biggest things that is also a feature that is valid for COMB potentials. We have only one element, only one parameterization for each element. Then we don't have many carbons, sp2 or sp3 or sp carbon. We have only one carbon in each parameterization. And the user doesn't define the number of bonds and who is connected to whom. The software is able to define that. The potential defines who is connected with whom. Okay. What's more? And this charge is initially it was equilibrated using the electron equilibration method, the EEM, that is connected with that idea that I explained before. Okay, let's see. Then here we have the components of this potential. We have a bond energy, contribution, lone pair, over coordination. This one is to avoid, for example, a carbon connected with 6 carbons. It's not forbidden, but the energy is so high that the system naturally goes to other situation. We have the angle, strain, under coordination energy. Then we have some specific parts for conjugation. Sometimes things that doesn't work as you expected. Then Professor Van Duyn included some terms, extra terms here, and so on, And then you have van der Waals and you have Coulomb. And also van der Waals and Coulomb are shielded. They have some kind of shielding when you go to really small distances in order to never obtain a really high energy that would destabilize the system. And then that's it. And here is a simple map of the elements they are parameterized in these days. Actually, I know that germanium exists, but I believe they didn't. I don't know if they published that yet. Some of these guys maybe as thing, I think also that I saw, but not published yet. Okay, and there is an interesting thing here. Even though you have, for example, cobalt, nickel, and copper, and neodymium, argonium, maybe you don't have both of them in the same parameter set. Then not all the pairs are available. Then sometimes you want to simulate, I don't know, fluorine with calcium. Maybe you cannot find that. Then you need to look in the literature. And that is one of the problems of React-FF, that you have many parameterizations. We have actually several branches of parameters, right? Initially in 2001, you had just one, and then you have this division here, a combustion branch. Here you have one kind of carbon that is kind of different from the carbon that you find here. But inside one parameterization, we have only one carbon, but you can have parameterizations that are different. what I mean. Then you have an independent branch for specific systems, and you have the aqueous branch in which we have surfaces with interacting with water, all those with water, okay, and so on. Sorry.
Previous slide you showed that the difference will have several terms, okay, but then you then you went up and have several branches. What terms there are on the equation there that plays the most important role for you to drive it to have different branches? What are the most good terms to drive them to say transport?
This is something that's hard to say in general because in each situation you have different problems. In some situations you have a problem with the torsion angles that is quite different in graphene or in diamond, for example. Then you typically, as I see, the problem are in the bonds and in the torsion terms first, then the other parts. Yeah, I think that, and there are some situations like conjugated systems was a problem in the past. That's why we have here an extra term that is not physically justifiable, not in principle. Sorry.
In line with the question made by I have another one. In the past, the equalization charge method, there was a problem due to the open polarization. If you have a huge molecule, you can have, for example, a huge dipole moment, and it's not physical. Is it correct?
In most versions, it's not corrected yet. I believe that it's being worked on, but I don't know the details of this specific problem. I know that Fanduin is with another kind of equalization of charges in the last few years, but I didn't have the chance to put my hands on it. But I should look into it. It's important just to know. Okay, let's see. We have the brands. Juarez.
How those brands, because brands, they was divided because different groups start different organizations, or those was a side strategy doing that?
Both things happen, but the one problem is that sometimes you have here in the combustion branch, you have a quite reactive oxygen. When you go to the aqueous branch, the oxygen is not so reactive as that. Then it's complicated to put water here, and it's quite difficult to adjust things. Then usually you have this problem, and sometimes some group starts the parameterization, goes there, oh, I have this here, can you help me? Like we do sometimes. Okay, then here a general view. Oh, sorry. Beryllium, I don't know. It's there for a long time. Nobody tried to do that. You have the interest to do that? Yes, that's all. Yeah, there is some problem, I suppose, but I don't know specifically what it would be. For example, I know that boron is a problem. Okay, for some years, but it's over now. SN? I don't know. I cannot. Maybe I can look into it. If you want to talk later, I can try to, but I don't know what are the substitutions that you are talking about. But in principle, it can make many of these descriptions, right? And here's some vision, some simplified vision of the algorithm that we use to calculate things with reacts. First, you have atom positions, then you determine the charge using the equilibration. Then you determine the bond orders to see who is connected to who. Correct the bond order. I will show for you some example of how this is done. Determine the angles and torsions and calculate the energy terms. Calculate separately the specific systems that I commented before, and then you have the energy of the system. You see that you have a lot of steps before you have the complete energy. And here we have an example of one specific parameterization for carbon and carbon, where I show how we calculate the bond order between these two carbons. Okay, we have here this expression. Each term here is related to this one is to sigma bond, pi bond, and double pi bond. Then the black line is the bond order. That is the sum of these three these three terms. Okay. Then the main contribution of the sigma pi is in this region. Here would be the distance in angstroms. Here, then we will start to have the pi contribution. Then you have here something like that. You'll see that the bond order goes close to 2. Then you have a double bond. And then you have the triple bond when you go in this distance, right? That is the idea. But this is also not completely efficient. Then to adjust to experimental data or things like that, it was necessary to correct a little bit the bond order calculation. Then this is the uncorrected bond order. And today we have some other terms to calculate to have the actual bond order. Okay, then the corrected bond order is described by this expression, in which we have inside the sigma contribution, the pi and double pi contributions here. Okay, then you see that many adjustments are made during the time, and we have many situations here to explain. And here, one example of how can we do a parameterization, just a really simplified explanation, okay? We define a training set, typically, and here we have the geometry of some molecules, and then for these molecules, what can we do? Maybe we will have, for example, a molecule that has a oxygen on one extremity, then we go and calculate the energy with this oxygen dislocated in many positions, and then we map these numbers here. Then I do that, for example, here we have the cobaltocene, the metallocene with cobalt, and for many deformations, and then I calculate the energy for each one of them, and these calculations are made using DFT. And after that, we do that for another molecule. Here, in this case, we have some BCC, FCC structures, because it included the cobalt and carbons. And then we have sometimes thousands of lines with many calculations and maps. Like if you could make curves out of this, right? With the energies of the system in many situations. Then, using this, we get an initial force field. Here we have a force field parameter file, and then we localize where are the parameters that you want to optimize. Then we have a script file in which we can define what are the specific parameters that you want to control, that we want to optimize. A GUO file in which we have many molecules that are optimized also, and then with these 4 files, we can make a new parameterization. Usually it's not too fast. You can take from some weeks to several months to make a parameterization, depending on the number of parameters that you need to adjust, okay? Here is an example. This is for carbon with fluorine. Here we have a comparison. Actually, this is mixed. We have the red one would be the reacts, and the blue one would be the quantum mechanical calculation for a parameterization that we used in one of our first works with reacts. Then here we change this bond distance here, and here we have this angle changed, and then we should make the red curve to fit the blue curve. This was the best condition that was obtained at that time. Let's see. This is other part of the same parameterization. You see that here we have other valence angles being changed, and here the dihedral angle that is not so good, but worked for our purpose at that time. Here is another example of a training set. This is for the cobaltocene. And then here, these are data for desorption energies for one atom, and then for a dimer on graphene. And things like that. You must do dozens or hundreds of this kind of calculations to be able to make a new parameterization. Right? Then now I will try to talk a little bit about some applications that we did using ReactFF and with our collaborators. One of them is Professor Galvão from Campinas, who was my advisor. He works with, and I work with computational simulations. Use a lot classical molecular dynamics and some calculations with DFT also. We have some, I will talk about some of these papers that we did together. Several of, all of them, they just discuss papers in which we used ReactFF, okay? Then we have this for about tribology, this one about unzipping big boron nitride nanotubes. Here about, this one discusses burning of graphene, a controlled burning of graphene in a specific situation. Here, some protection of nano cones of metal using nano cones of carbon, and the unzipping of carbon nanotubes, and some other stuff here. Here are some works in collaboration with Professor Van Duyn. I will discuss a little bit of some of them. And other collaborators, Professor Stanislav Moshkalev from Campinas. Our last work was using ReactFF also, even though there were no chemical reactions in this simulation, but we didn't know if they would happen or not. It is the nanopolishing problem. We have a multi-layer graphene patch here and on some kind of metal, and then if you heat this up, it makes really nice polishing here on the surface, and it improves the thermal transport and the electrical transport on the system. If I have the time, I will talk about a little bit about it. Here is one of our nice work with reacts. Professor Moshkalev had this suspended graphene, and then these are multi-layer graphene suspended, and then he was able to burn layer by layer this graphene using lasers. But he didn't have a model to describe why the burning was in the perpendicular direction to the laser beam. Then we did a nice atomistic model, and it could describe quite well the data that he obtained. And then we saw that the system burns one layer, and then another layer, it starts to be burned just when the first is almost finished. Okay, I had a nice movie about this, but it's not here today. Another important work is about this kind of system. We have graphene, and graphene being hydrogenated and fluorinated. In the first case, we can make graphene. In the other case, we can make fluorographene. Then here are React-FF description. Here we have the relative charge on the system. You see that you have rings with alternating charges. When you put a fluorine atom here in some connected to some carbon. Here is the fluorination dynamics for 2 different temperatures. A description with that parameterization of fluorine and carbon that I discussed a little bit a few minutes ago. Also, we see that the comparison between the lattice constant for graphene and fluorographene. And then here, this is the new information that this paper brought. That is, if you have in the system hydrogen and fluorine, the fluorine will increase the hydrogen capturation of the system. And we will see this in a few minutes. And we also found, this was quite interesting, we found some specific configurations. Here, yellow are hydrogens and red are the fluorines. We saw some specific organization of these atoms on the graphene membrane. And these configurations were confirmed later using DFT. Then it's a case where things were inverted, right? Instead of DFT saying for us what is the structure, and then we confirm that we can reproduce that, we found it then and then saw in DFT that it was true. Okay, this is the paper. Here are those fittings that were done for this system. Sorry, here I have a video that I need to show. This is the formation of fluorographene. That is a mixed structure of carbon, fluorine, and hydrogens. And then here we can see the red ones are the fluorines. Then after one fluorine arrives, we have always a hydrogen on the other side. And then hydrogens will start to accumulate close to these structures. Why? Because the fluorine comes here, deforms the lattice, brings some sp3 hybridization in the region, and then it becomes more reactive, and then the hydrogen connects easily. Okay. Then we have several small domains formed, and then we will show one of those structures that I cited here. We have a chair configuration here. Okay. Let's go back. Right. This is another one. I forgot that I had this one. Let's see. Here. Here, the idea is that we fluorinated the graphene membrane first, and then later we released only hydrogen on the chamber. Then we see that the hydrogens attach almost exclusively close to the fluorines. That's the idea of catalyzation of hydrogen capturing by the fluorine. Okay. We see big domains here. Right. Let me close this.
This last thing that we show, for example, when you have the first two, second, or third hydrogen that goes to fluorine, I understand. But some of the hydrogen is getting bind to the next hydrogen, that's probably like a more ion of a hydrogen. How can we understand this effect? Because the good interaction is very strong. Hydrogen and fluorine, but there's a screening now.
Yeah, but this is a known effect. Before this work, there was some investigation about the graphene, that is just graphene with hydrogen. And then they noted that when one hydrogen attaches, it catalyzes the hydrogenation for other guys. And then we will have big monocrystalline domains made out of hydrogen, because the small deformation that it causes facilitates the attachment of the new ones. Then it's the same thing here. We have some hydrogens around the fluorine, and then after something is constructed, the increasing the growth of this hydrogenation is just like in the graphene case. Yeah. Yes, yes. No problem. Here is the polishing system. As I explained for you, initially we just knew that experimentally, when we put this patch of graphene, it attaches to two leads, for example, when it is heated. And one of the questions was, could we find here some kind of carbide with the metal? The metal could be platinum, gold, or iron, anything. And then we did some simulations using gold and nickel, and we saw that even nickel, that is really some element that really likes carbon, we didn't have the carbide formation in here, okay? And then Reax was able to explain this nicely. Here another example. In this case, we don't have many reactions, right? We have actually something that's dominated by van der Waals interactions. That was this adsorption of argon atoms on nanotubes, on small single-layer nanotubes that was found experimentally by these guys that collaborate with Maurício Terrones, and I did simulations using ReactFF to show how are the configurations that you can find here. I can show to you, just 1 second. Let's see. Here, it's a system in something around 20 Kelvin. And then you see the argon freezing on the surface and forming something really well organized, you see. Yes. And we have also a bundle of carbon nanotubes. Then you see the carbon nanotubes sticking together, and then the atoms starting to interact and go into the grooves and being captured. It's really nice also. Right? Yes. 20 Kelvin. Yeah, they put the argonium really ready with low pressure on the chamber, and the experiments were made with this temperature. Okay. Well, this is also something that is somehow, in some sense, expected, because the force that drives it is van der Waals interaction. And it's known that if some atom or molecule passes the barrier of the tip of the tube, inside the energy is lower than outside. Then there is like a small energy well where the particles can be trapped there. If you increase too much the temperature, some of them can go out again. Yes. Just because we would like to see if some of these boards could connect or not, you know. You didn't know what was going to happen. Then we did the same simulation using closed nanotubes to see if the argons are assume the same configuration outside, and it was the same thing. Yes, I used the typical radios that the experimentalists passed to me as information. No, actually, the biggest one, I think it's more favorable, because in the smaller one, even though we saw here they go inside, but statistically it's not the case, because in the tip you have a repulsion just in the frontier sometimes, depending on the size. How much time do I have? Okay, that's cool. Okay, this is a nice example. Another one is the gold tip enhance. The mechanical enhancement for gold nanotips. This was made in collaboration with Professor Adojorio and Professor Galvão. The problem of the experimentalists was that they have a gold nanotips for a microscope, and then they were losing many tips, because any experiment that you do, this is too soft, right? Then the idea was to see if using a carbon nanocone things would work better, because the carbon nanocone is conductive in some cases. I don't know if you have all of them as conductive, but probably. And then we did some simulations to see how would be the mechanical behavior of the system when we have this small cap. I think I have some, yeah. And then here we see the data, and I have some simulation here just about this. Let's see. First, only the tip. What happens, obviously it will be deformed, and then it will be irreversible, right? When we pull the tip back, it will be completely defunctionalized. It will not be functional anymore. And then we can compare this with a capped nanotip. Let's see. Here. Then with the carbon nanocone, you will see that the tip of the carbon nanocone will fold, and then magically it will unfold when the pressure is released. That's why we used the ReactFF here also, because we didn't know if we would have some type of reaction here. We have a little bit of deformation, but the general form is preserved. Okay, let's see. Right. Another example here. This work was a mixing. We predicted the existence of several new fullerenes made with carbon or boron nitride, and then I did this with a quantum method, and then we used a ReactFF parameterization for boron, nitrogen, and carbon to study some properties of these systems. I think here my video is not so good. It's a compatibility problem here. But we see that in this fullerene specifically, the hydrogen molecules are captured, and after captured, it's not frequent that they go out. Then we can see that we can maybe capture some kind of gas in this kind of structure, okay, and they are quite stable. And we have also a nice paper regarding this kind of fullerenes with Professor André that will talk just after me. I don't know if he will show something. Okay, and here are some data for the gas encapsulation. Let's see the paper. Let's see. And here another example. Here we can see the diffusion. Here we have a nitrogen and a hydrogen inside the porous nanotube. And we see the diffusion of one gas. One of them is escaping, and the other one is trapped inside this porous nanotube. Also using ReactFF. This is not part of a published article yet, but we are working on it. Okay, and the last example, the unzipping mechanism. The idea is that sometimes the experimentalists can get a nanotube and unzip it to make nanoribbons. And then we were studying how this process happens, how are the mechanical stresses happening in the system. And here we have a demonstration of I will use another, but I'm sorry. Unzipping. Okay, here. Here we have 3 different chiralities of big nanotubes with big defects, right? Big rips here, and then we are going to induce mechanical stress on these systems, and then we see that the stress profile is quite different from one to the other chirality. Okay, and this was also with ReactFF, and the stress that we are showing here is the von Mises stress. That's it. Let's see. Right. This was published in PCCP. When we did this for carbon nanotubes and then for boron nitride nanotubes, and this one was the cover article of PCCP once. And now, just to finish, just some conclusions. We see that reactive simulations based on this kind of systems this kind of potentials are really powerful. We can do simulations including reactions and simulations where reactions are not present also, and describe well both kind of systems. Several new materials can be described with this kind of methodology. And one important thing that I would like you to remember is that Tersov potential is the origin for many, many new descriptions that we have today. COMB potentials and ReactFF potentials are based on Tersov in some sense. And the charge equilibration is something that is really important and fundamental for nice descriptions. Okay, well, that's it. I would like to say. Thank you.